Okay, so what I'm going to talk about in this video is simultaneous equations. So what that means is basically if you have two variables in one equation, we're going to need to solve for them. Okay, so let's take an example straight away. Let's go x plus y equals 5 and x minus y equals 1. One thing I want to talk about is that we have two methods to solving this. One of them is elimination, and the other one's substitution. I'll start with elimination, then we'll do substitution for the same question to show the difference between them, and then I'll try to take the concept and apply it to something uh, a little less algebraic and well, it'll be the same amount of algebra, but a little less mind-numbing, a little more real world, I guess. Okay, so let's start with elimination. The idea around elimination is that we get rid of one variable straight away. Actually, that's the idea about both of them. We have to get rid of one variable in order to solve for the other. You might be wondering why that's the case. It's because if you're given any equation with more than one unknown, any singular equation with more than one unknown, take this for example, it's impossible to solve. If I give you this equation and I ask you what is x, it's impossible. There's nothing you could do to tell me straight away that x is a number. It's not possible. I'd have to tell you that y is 3, and then from that you could figure out what x is. Only with that much information. If I didn't tell you that last part though, if I just gave you that one equation, you would not be able to solve it. So we're thinking, seems to be the problem here, isn't it? We have x plus y equals 5. That's two variables in one equation. But the thing is, we have one equation and another equation. So given that we have the same number, so the number of variables matches the number of equations, if this is true, then it's solvable. So since we have x and y, two variables, and 1 and 2 equations, this is possible. Now I'm going to teach you how, but it's important to know if the question is even possible to begin with. Okay, so elimination is fairly simple. You'll either be adding or subtracting the two equations from each other. So in this case, I would add, and this is really simple addition. It's basically what you do if you were doing like year 3 sort of subtraction or addition. You just kind of go through the units column, go through the tens and the hundreds column and do them individually. So I got 5 plus 1, 6, y minus y. You see that? Positive y minus y. What happens when I have like positive y minus y? It's like positive 2 minus 2. I get nothing, right? So I could put a 0 here, right? I don't have to put a 0 there. I could just leave it empty. But just for illustration purposes, I'm going to do that. So yeah, y plus minus y is really y minus y, and the result of that is 0. So this column will be x plus x. That's just 2x. So I have 2x plus 0, so that's kind of just useless. I can scribble that out. You don't need that. I got 2x equals 6. If you take a look at what's happened, we've gotten rid of a complete variable. It's not, y is not there anymore. I've got one equation. I've got one variable. So now I can just solve. So dividing by 2 on both sides, I'll get x equals 3. So it might look like, I'm going to switch to another pen. It might look like we're done because we have x equals 3 and it's usually find x, but that's not the case. With simultaneous equations, however many variables, in this case 2, we have to solve for all of them. So since we have 2, we have to solve for y as well. So this is the second step in the process is sub back in. Where do we sub back in? Well, you can sub 3. You can sub x equals 3 because you now know x is 3. So everywhere there's an x, you don't need to put an x. You can put a 3 instead. You can sub it into either of these equations that you've been given. Doesn't matter which one because they both describe the same letters. So you could sub it into the first one or into the second one. Personally, I'm just going to sub it into the first one. So we're going to get 3 plus y equals 5. One equation, one variable. Move the 3 to the right. We'll get y equals 2. Now, hopefully we're happy with that. These are your two solutions to the problem that we were given, right? We've solved both of them. How can we check? Well, you can run through the whole process, make sure you haven't made any mistakes. But you should do that, but you should also sub into both of them. Sub in x and y for numbers instead. So you have 3 plus 2. Is that 5? Yes. So we know it works for that. 3 minus 2, is that 1? Yes. So we have satisfied the requirements and we have solved correctly for x and y. Okay, so that was elimination, and the things we looked out for there was we were either adding or subtracting these equations. The reason, I guess I should explain, the reason I added the equations is because I knew that if I add, then these two things would disappear. Can you see that? That these two things would disappear. If I had subtracted, I would have gotten y minus y. What happens when you have a minus and a minus next to each other? Well, when they multiply, when you know you have a negative times a negative, you get a positive, right? So you would have had a y minus minus, which is really y plus y. And if that was the case, then I wouldn't end up with nothing here. I would end up with 2y. And that's not good because the result of that is you end up with 2x plus 2y equals 4. None of that's important. All that's important is that we didn't cancel any letters out, and so we still have 2 letters, and that's a problem. We don't want 2 letters. So subtracting wasn't the go. Adding was, because I can clearly see that if I have y minus y, I get nothing. Okay, so make sure you're being careful with that. You're not always going to add when you come to elimination. And you don't always have to get rid of y. I just did. Okay, let's talk about substitution. I'll do that in green, so we know that it's a different method. Okay, so with substitution, the first step is to make one of the unknowns, either x or y, make one of them the subject. What does the subject mean? It means to make it along the lines of y equals something or x equals something. Just keeping in mind that that something can be an expression, has to be an expression. It will not be a number, not just a simple number. So don't worry about straight up finding y equals a number, because that would defeat me explaining this to you. So I'm going to take the second equation. Okay, I'm going to do x minus y equals 1, and I'm going to try and make y the subject. You could pick any of the letters. You can make x the subject of the first equation. I've just happened to pick y the subject of the second equation. The way I'm going to do that is I'm going to move this y to the other side, and I'm going to get x equals 1 plus y. Well, actually, what we notice here is we've already made x the subject of the equation. So I think we'll just stick with that. We'll just stick with making x the subject of this equation. Okay? So this is a super important point. We've made it the subject. We haven't eliminated anything. So we're still not in a good spot, but it's one step further. Okay, so now that we've done this, keep in mind that we got this from the first equation. We then need to take this thing that we've made, and I kind of call it 1 star because I call it 1 modified because I modified the first equation. I'm going to take 1 star and put it into the second equation. Do not sub it back into where you started. You can try it and see what happens. Okay, so we're going to sub it into the second equation. So wherever I see an x, I'm no longer going to write an x. I'm instead going to replace it because x is 1 plus y. I'm going to replace it with a 1 plus y. So let's try that. Oh, sorry, I made a mistake again. What we've done here is, sorry, this is not 1 star, this is 2 star. So we got this from 2, 2, 2, and we're going to sub that into 1. Right? I got this equation from here, not here. So we modified it to make it the subject, and we're gonna take this modified thing and we're gonna put it into equation 1. So everywhere we see an x, we're gonna replace it with a 1 plus y. So it's gonna be 1 plus y because of this x, and then another y, so another plus y, and then an equals 5. Okay, and then we'll collect like terms because it's silly to leave them unattached to each other. So we're gonna get 2 lots of y, move the 1 over, we did that by subtracting because it was positive. This is 2 times y, so to get rid of the 2, I'm going to divide by 2, divide by 2. So we get y equals 2. And you can see here that we have y equals 2, which is the same solution we got from elimination, which is good, because if they were different, we would have made a mistake somewhere. Are we done? No, because as we said earlier, simultaneous equations, got to solve both variables. will stay green. The good thing about substitution is it makes the second part, the subbing back in, easier because we made one of the things the solution, the subject, sorry. So here you see x equals 1 plus y. All we need to do is put the number that we now know for y in there. What's y? It's 2. So therefore, x equals 1 plus 2, which is 3, and you found the other value, which we got over here. So those are two different methods. This is, I should probably have labeled it. This is elimination, put that in purple as well, elimination, right? And this is I'll put that in red, substitution. Okay, so both of these methods are super useful, and they both get you the same answer. Okay, it's just in certain situations one will be quicker. Personally, in this situation, this example, elimination I think is quicker because immediately I can see that these y's will cancel out if I just add the two equations. That will give me x immediately, and subbing back in is a little slower than this one, but I get a variable very quickly. It should be true that in pretty much every scenario you can use both equations, both methods, and you'll arrive at the same solution. It's just that one will be quicker in nearly every situation. Okay, good. Okay, let's think about a problem, I guess. I'm going to clear these. Let's think about a problem. So let's consider that there are two cars and they're at Macca's. Okay, they're at Macca's. I could have done that in, actually, what color? I don't, it's a golden arch. What am I doing? So let's go with a golden McDonald's sign. Okay, and we've got two cars. I can't draw, so I'm going to make one car a black dot, and I'm going to make the other car a purple dot. And they are trying to, they stopped for a lunch break, and they're trying to make it to this mount. Okay, they're trying to make it to this mountain over here. Blue. Okay, so we're trying to get from here to here. We got two cars. Question is, one car happens to leave 4 minutes. Car, okay, we'll call that A, call that B. Car A leaves 4 minutes before, so it leaves earlier, right? It's the first one out. It leaves 4 minutes before, oops, car B. Okay. They are, let's say, 100 kilometers away from their destination. Now, some of you might be American. You can kind of ignore the units. It's not particularly relevant. It's mainly the number, 100 distances, let's say, away from the mountain. 4 minutes before car B. Right. So so car B is traveling. So the speed of car B is 60 kilometers an hour. Oops, kilometers an hour. And speed of car B A is 50 kilometers per hour. Right, so what we can see from here is that, imagine a situation where a Macca's, car A leaves first, but it's traveling a little slower. Car B has to catch up, so obviously it travels a little faster. Right, so the question then is, when do they meet? How long? That's a better way of saying it. How long does it take for them for car B to catch up? How long for car B to catch up? Let's think about that. Okay, so what we can do is model this entire situation. We'll put that in green. Model this entire situation with simultaneous equations. This is a little more complicated, so don't worry if you're a little confused here. Go back and attempt some of the simpler simultaneous equations, and then come to this question, because this is an extension. So let's model car A. Okay, so car A's distance from the starting point, we'll say this is the starting point, so it has a distance of 0. over time, okay? And we need to define time, so this is getting a little funky. Okay, so the distance of car A is going to be some equation that we need to find, oops, and the distance of car B is going to be some equation that we need to also find, also write out. Okay, so car A is traveling. We're also going to need this idea. Hopefully you guys are familiar with speed equaling distance over time. That's a formula that you could memorize. I like to think about it just with cars. It's fairly simple. How do you read the speedometer? Might be 70 kilometers an hour. It might be 30 miles an hour. But the point is, it's always speed is something per hour, right? A distance, kilometers or miles, whatever it may be, per time. So you get d on t. So speed is d on t. Now, in these equations that we're writing here, we're solving for distance. So if you were to rearrange this, you get d equals st. This isn't super important how the algebra works and everything, but we're modeling linear simultaneous equations. So what we have here is a speed and a time. We don't know anything about the time, but we do know about the speed. Car A has a speed of 50 times time, and car B has a speed of 60 times time. Now we have to do something a little different here. We're close, but we have to do something a little different. We know for a fact that car A leaves 4 minutes before car B. So what does that mean? Because if we take a look at these equations currently, this would mean that after 1 second, how far would dA have traveled? Sorry, after 1 hour, how far would have dA traveled? It would have traveled 50 kilometers. After 1 hour, it would have traveled 60 kilometers, right? After 0 time, this would have been this would have been at 0 distance, and after 0 time, this would have been at 0 distance. But that's not true, because car A needs to be 4 minutes ahead. So the next question is, how far ahead in distance is car A from B? So try to answer that. How far ahead in distance, not in time, in distance is car A from B? Well, you know he's 4 minutes ahead, so that's a time. So if you go up here, if you go here, you know he's 4 minutes ahead. You also know how fast car A is traveling, right? He's traveling at 50. So if we know he's traveling at 50 kilometers per hour, and we know that he's 4 minutes ahead, we could figure out the distance, right? So how we could figure out how far ahead he is. So he is 50 times not 4, okay? It's 4 on 60. Why is it 4 on 60? Because there are 60 minutes in an hour, right? So we get 200 on 60, which will work out to be 3.3 reoccurring kilometers. That's how far ahead he is. So we need to add that in here, 3.3 kilometers. Oops, don't need to write the kilometers part. Okay, so now when you sub in 0, the distance of car A is already 3.3. So he would have already started. He would already be 3.3 kilometers ahead. Do we need to do that for dB? No, because it doesn't leave earlier. It's not going to be traveling ahead. So we're defining time. We define time, or t equals 0, more specifically, when B leaves. Okay. So when B leaves Macca's, that's when we're starting our stopwatch. Okay. So all that gibberish, all that work, mostly will be given to you, especially if you're in year 9 and year 10, maybe even year 11. Depends. So not too bad there. So let's just get rid of all this. We have a bit more space here. Okay, we're going to need these equations though, so we'll keep them. This is the start of the simultaneous section. The first part was linear modeling of the whole entire situation, which is a little complicated, admittedly. Now we start the process. What do we have here? We have two variables, d and t, d and t, like the y and x from before. We just need to solve them simultaneously. Here, substitution is the superior method. Why is that? Well, if you take a look, if you remember, substitution was about finding or making one of the variables the subject of the equation so that we could sub it into the other equation. But if you pay attention, both of them are already d equals something, right? So all we have to do is sub d, and we can get rid of, oh, well, there's actually one bit of information that I've missed out. We can almost sub these in, but are these the same? Is the distance of the car, distance of car A, the same as distance of car B? Not always, right? So how can we deal with that? Well, what's the question? The question is, when does B catch up to A? So what will the distances be at that point? If B is caught up to A, the distances are going to be the same. So there won't be a difference between DA and DB. It's actually the exact scenario we're looking for. So we're going to get DA is equal to DB, and so we can kind of just not represent them as different variables because they'll be the same thing. So we'll just have D and D. Why is that useful? Because now we have dt, dt, and we can set these two equal to each other. So what we'll get over here is that 50t plus 3.3. Okay, so this section, if this is equal to this, then this must be equal to this, 60t. And what you'll notice is finally, we've eliminated every variable but one, and we can solve for that one variable. So we'll move the 50 to the right, simply because this number is bigger. So we get 10t equals 3.3, and we'll get t equals 3.3 on 10, which will roughly equal, I could definitely just move the decimal across, 0.33. 0.33 what? 0.33 hours. We would keep in mind that all of our units started as kilometers and hours. So we'll get 33 hours, which is roughly, no, it's exactly 20 minutes, right? So in 20 minutes, car B will catch car A. Okay, so hopefully that example didn't go too badly over your head. It was a little confusing to model the process, but the last part itself was just the simultaneous part was solving for t, which was eliminating through substitution. You can also, by the way, sub that back in to figure out where they are, right? Because usually you find x and y, so you could sub your t back in. We just write t down there, so we know that that's t. You could also sub t back in to find d. And once again, you can sub that into either of the equations to solve for d. In fact, you could sub it into both and check that they get you the same result, which would ensure that you've done it correctly. So a little bit of a complex question, but very practical. I personally had this exact same situation when I was going to the snowy mountains. So attempt it in your own time, change the numbers a little, see if it makes sense, follow the thing step by step, and let me know how you guys went with it.